Hello, in this lesson we are looking at circular motion on banked roads. We look at two cases, without friction and with friction. For without friction, assume that this is the banked road which is banked at an angle theta with respect to the horizontal direction. That is the object moving on the circular motion, and that's the reaction of the surface or the road, and this is the weight of the object, and that will be the radius. In vertical direction, we have no acceleration, so the net force must be zero. What are the forces acting in the vertical direction? One is the mg, which is totally in vertical direction, but r can be resolved into two vectors, r cos theta and r sin theta. Remember that r makes an angle of theta with the vertical direction. So that becomes r cos theta, which is vertical, and r sin theta, which is horizontal. Now, r cos theta must be balancing mg to have a net force in the vertical direction. So r cos theta is equal to mg. From here, we can work out r to be mg on cos theta. The only force towards the center and horizontal is r sin theta. That will be our centripetal force. So using the formula for centripetal force, which is Fc is equal to mv squared on r, we can replace Fc with r sin theta, which is the only centripetal force we have, equal to mv squared on r, and replacing r with this value from here, mg on cos theta, we get this mg times sin theta on cos theta is equal to mv squared on r. Sin on cos is tan, so we get g tan theta is equal to v squared on r after cancelling m's from both sides. And that gives us v squared is equal to rg tan theta, and v is equal to rg tan theta. That is the maximum velocity at which this object can negotiate the tail without slipping. Now for case 2, where we have also friction. When we have friction, we got to put it in the direction that will help with the centripetal force, because we want to see what's the maximum velocity we can go at. And the centripetal force, friction force will be along the road like that. So now we have three forces acting: reaction, weight, and friction. Again, if we resolve r, will be r cos theta vertical and r sin theta horizontal. Force of friction, as you can see, make an angle of theta with the horizontal direction. So its horizontal component will be ff cos theta, and its vertical component will be ff sin theta. Again, we have no acceleration in the vertical direction, so that means all forces down must be balancing all forces up. The only force up is r cos theta, and the forces down are mg and f of f sine theta. So these two together down, this one is up, so they must be equal. But also remember that force of friction is equal to the normal force or reaction force times by the coefficient of friction. So here I replace f of f with mu r. I get mg plus mu r times sine theta is equal to r cos theta. From here we make r the subject, and we get that r is equal to mg on cos theta minus mu sine theta. Now we look at the horizontal direction. In horizontal direction, we have two forces, f of f cos theta and r sine theta, both of them acting towards the center. So r sine theta plus f of f cos theta is equal to mv squared on r. Remember, we can replace r with this expression, and we can replace f of f with mu times r. So mu times that. So that will give us here mg on cos theta minus mu sine theta. This whole is r times by sine theta plus f of f is mg mu divided by cos theta minus mu sine theta. That's f of f times by cos theta is equal to mv squared on r. From here, you make v squared the subject after cancelling m from both sides, and you will get an expression like that: rg sine theta plus rg mu cos theta over cos theta minus mu sine theta. And square rooting will give you this expression for velocity. Again, this is the maximum velocity that the object can move at on a circle on a banked road without skipping the road. Thank you for your attention.